Hi, this is my video number 27. Video number 27. Alright. So I'll talk on green theorem. Okay, green theorem. So this green theorem basically give the relationship between line integral and around a closed curve, around a simple closed curve C, and a double integral over a plane region D bounded by C. Okay, green theorem. So what is this? Basically, for example, we have the functions, the curve, something like that. Okay, in the previous case, we have to split this C1, C2, C3, right, to integrate C f dot dr. Okay, so we have to consider each of this curve. So for two-dimensional case, you know that this is just a p dx, p of course xy dx plus q xy dy. Okay, now we need to, the green theorem says if we have a closed curve like this, or you have a circle or whatever it is, as long as it's closed curve and PQ are continuous, then we can use double integral. There is a relationship between this line integral with the double integral, and those using the double integral should shorten the computation as well as make life easier. Okay, so what the theorem says? Green theorem. So let's see be a piecewise smooth simple closed curve and positively oriented, means it shows clockwise direction. Okay. In the plane and let D be the region bounded by C. The region bounded by C. If P and Q have continuous partial derivative, on an open region that contains D, on an open region that contains D, then the line integral over c p dx plus q dy, this is equal to, we integrate over the region D, double integral del q del x minus del p del y dA. So this is the Green theorem. You remember this one? Okay. Now let's prove this. Let's prove this. Okay. So we consider C like that. Let's say this is our C. This is C1. This is C2. Okay. So let's say C1 given by y equal to g1x and C2 given by y equal to g2x. Okay, and C is simple closed curve. C is simple closed curve. Simple closed curve. And piecewise smooth and positively oriented, as given in the statement of the theorem. And PQ and its partial derivative mean del P del Y, P Q del P del Y del Q del X, all this continuous. Okay, continuous. Okay, so from the Green theorem given here, if you look at this carefully, so what we can see, this, if we can show this is equal to that, this equal to that, then we're done. We add up, then we're done. Okay, so I can write this. Let's make it, let's go to the other page. Okay, so this is the Green theorem, P dx plus Q dy over D del Q del X plus del P del Y, minus dA. That's a Green theorem. Okay, this is our region. Write that. This is C1, y equal to g1x. This is C2, y equal to g2x. Okay, direction positive oriented, and on x we have A, B. Okay, so if I can show that P dx over C, this is over C. Okay, P dx. P, remember P is xy, so I put P xy. Dx is equal to negative of D del P del Y dA, and C Q xy dy, this is equal to integrate over D del Q del X dA. Okay, if this is equal to that and that equal to that, and then we can add up together, this one, then we will give this relation. So we're done. So let's give a name. Let's call this is 1, let's call this is 2. Okay, and the region D here, the region D is given as all xy such that x between A and B, and y g1x g2x. Okay, now if you use this from 1, consider the right hand side of 1. Okay, we consider first right hand side of 1. So right hand side of 1, we can ignore the negative, because negative we can add up later. From the right hand side of 1, we integrate over d del p del y dA. This is nothing but, okay, look at d. Look at d. So d, this is your d. This is d. Okay. So we use for this region, we integrate for double integral, we integrate y from g1, that one, into to g2, that one, and x from a to b. Okay, let's write those things. So we integrate x from a to b, y from g1x to g2x. Okay, del p del y, then now integrate with dy dx. Okay, now we integrate del p del y, we integrate respect to y, what left is just p, and then we substitute the value for g. P is xy, yeah, p is xy. So this is, you can evaluate those things. So what we have, integrate a to b, that what left is only p. We evaluate at those points g2, g1. So we have x g2x minus p x g2 g1 x dx. Okay, you can put big bracket there. Alright, so we have those things. Now if we consider the left hand side of 1, left hand side, this is 1 that I gave a name earlier. We have considered the right hand side. Now we consider the left hand side. Okay, for left hand side of 1, remember that for the left hand side, we integrate over the curve C, and C we have 2, C1 and C2. So in this case, our C is C1 and C2. Okay, so for C1, if you integrate those, C1 p dx, pxy dx. Okay, so this is just, we integrate, look at C1, this is C1, our C1 y equal to g1x, and x from a to b. So we transform here, x from a to b, p x, y we substitute with that function, which is g1 x dx. Okay, and for C2, that for C1, for C2, and if we integrate C2 pxy dx, this is, look at C2 from B to A, and along the G2, y equal to G2. So we transform to this, we have integrate from B to A, p x, this is g2x dx. Okay, now if you make it if you make the limit of integration same, so what we have here, this is just negative of a to b p x g to x dx. Okay, now so therefore we have integrate c p dx of xy dx. This is just, we add up those two, p xy dx plus c2 p xy dx. Okay, use the one that we already obtained. So we have here, we have integrate a to b p x g1x dx. Okay, plus integrate, so a minus here, minus a to b x g2x dx. Okay, we can rearrange this. Remember that for equation 1 here, for equation 1 we have negative. All right, we have negative, so I can put this negative. If you look at the right hand side of 1 that we obtained earlier, right hand side of 1 here, so we got this a to b p g2 minus g1. You see, g2 minus g1. Here we have g1 minus g2, so we can put the negative out. We can take the negative out, so a negative a to b. We have this function because we wanted g2 first. Oh, missing here p. So we have p x g2x minus p x g1 x dx. Okay, so let's call this equation star. So from here we have shown that not this one. From here we have shown that the equation 1 that we named earlier agree with, we have shown that this left hand side agree with the right hand side. Now we move to the second part. Okay, for the second part, so from that what we have, c p xy dx, this is equal to integrate negative of del p del y dA. We have shown this. Okay, next we need to show for the second part here. Okay, to show that, so which means we need to show that the second part is integrate q xy dx is equal to d del q del x dA. So I left this part as an exercise to you. Okay, DIY. So I have proved this. I leave it to you to prove that one. Please do. And then we add up these two. Okay, add up these two. This is from the equation 1 that I put earlier. This is equation 2. Then we add up those 1 and 2 that give us integrate c p dx plus q dy. This is integrate d del q del x minus del p del y dA. Right? This is the green theorem. So let me give you an example. Okay, let me give you an example. Let's say we want to evaluate C x squared dx plus xy dy, where your C is given as a triangle 0, 0, 2, 1, 0, 1, 0, 2, 1, 0, 2, 0, 1, 1, 0, 2, 0, 1, and 0, 1, 2, 0, 0, 0, 1, 2, 0, 0. So if we sketch that C, what we can see that from 0, 0 to 0, 1, 0 here, this point to here, okay, and then 1, 0 to 0, 1, 0, 1 is here. So we have this line that tak lurus, that and that. So that's our C. Okay, and yeah, you should recognize this line here because this is 1, so this is 1. So this equation is y equal to 1 minus x. So it's not difficult for you to evaluate this. So this is closed integral. The important thing is this is closed integral. And if you look at the P and Q, if you differentiate, the P is continuous, Q is continuous. If you differentiate P, we have 2x, right? We differentiate P with respect to y, you got 0. Differentiate Q with respect to x, you got y. So both continuous. Yeah? So you can use the Green theorem. So in this case, we have P is x squared. So therefore, we have del P del y, that's 0. Q is xy. So del Q del x, this is y. Okay? If we integrate this using a line integral, we need to consider each of these curves, C1, C2, C3. Now, if we use the Green theorem, so we have PQ already there. So therefore, we use the Green theorem that we have integrate over region D. Where is D? This is our D. D is region bounded by C. Okay, you substitute those del Q del x, del Q del x. Don't get confused with this. Del P del y, dA. Right? That give you. Okay, so del Q del x is y. Del P del y is 0. Del A, so you have region on xy, so this is d dy dx. So y from, look at our region here, y from 0, this line here is 0, to that line connecting 1, 0 and 0, 1. So which is 1 minus x, and x from x 0 to 1. So x from 0 to 1. So you can evaluate this easily. Alright, so I think you can proceed this no problem. So that gives you 1 over 6. You can verify this. Means we use a line integral, use Green theorem, okay, double integral, these two must give the same value, so you can try that. I'll give you another example. Let's say if you want to evaluate C, 3y minus e sine x dx plus 7x plus y4 plus 1 dy, okay, where C is given as x squared plus y squared equal to 4. You could recognize this. This is a circle of radius 2. So we have 2 here, 2, negative 2, negative 2. So you look at the integrand there, you look at P, you look at Q. If you use the line integral, it's not easy for you to integrate this. It's not easy. Okay, you need some substitution and so on and so forth. Alright, but using the Green theorem, you can recognize this. This is using the Green theorem. We integrate over region. Alright, this is our region D, so we integrate over region D. Okay, del Q del X, del X 7x plus y4 plus 1 dy, del Q del X minus del P del Y, our P is 3y minus e minus positive sine x dA. Okay, put big bracket there. So you can evaluate this. This is over region D. Differentiate with respect to x, you got 7. That's all. This one, we integrate with respect to y, we got 3 dy dx. Okay, this is a circle, so for the circle we use polar coordinates. Remember that one, circle we use polar coordinates. So for polar coordinate, what we have, x is r cos theta, y is r sin theta, dx dy is r dr d theta. Okay, so the integral free of x and y. So what we have now, this is 4, we can take out 4, we integrate our r from 0 to 4, 0 to 2, okay, because radius of this is 2, theta, this is full circle, theta from 0 to 2 pi, okay, and then we have 4, then dy dx is r dr d theta, so r dr d theta. Then again here you can do it, I leave it to you, so I think you get the answer is 36 pi. Okay, to end this video, I leave to you this as an exercise. Number 1, let's say we want to integrate C, minus x squared y dx plus x y squared dy, where our C is given as x squared plus y squared 4 1. So I think you can recognize this. C is a annulus. You have 1, you have 2, so this is our C. This is our C. So this is radius 1, this is radius 2. So if you transform using, look at this, this is closed integral. Inside that, this is continuous, differentiate respect to y, continuous, differentiate respect to x, continuous. Sorry. Sorry about that. So we have you know what happened? Because the smell from the kitchen. The smell from the kitchen. All right, so we have those things. What is it? So this continuous, differentiate respect to y, continuous, differentiate respect to x, continuous. Then you can use the green theorem because this is closed integral. So use the green theorem. And number two, integrate c x plus y squared dx plus y plus x squared dy, where c given as y equal to x squared and y minus x plus 4 and x equal to 0. I don't want to show you this the curve C, but I want you to sketch yourself. All right, so with that two exercises, please do this exercise. So I end up this video number 27. All right, bye bye.